Have you ever wondered if Rust is better than C++, or maybe the other way around? I'm Sonia, and you're welcome in C++ versus Rust, C# special. Yes, today we're gonna talk about C# implementation of our NodeGraph. C#, we're gonna bring our C++ and Rust design into C#. We already implemented the same design in Rust and C++, and now we're bringing it to C#. Let's see if that's possible. Let's see how this will look in C# using all the C# features, such as covariance. Let's look at this. This is our C++ code. We did this evil thing. We renamed the shared pointer to arg, weak pointer to weak, and enable shared from this to enable arg from this. Okay, so that it sounds and looks a little bit more rusty. We have this graph pin, okay? We have this iGraph node, right? So these are our interfaces. We can see that in iGraph node, we have input pins and output pins enumerated as a set of iGraph pin pointers, which are args of read-write-lock of graph pins. So this is actually interface of read-write-lock, interface of graph pin, okay? So that's an interesting thing, and we have an arg. Now, how are we going to implement exactly this bit in C#? Let's look at this. So this is C# code. This is our pin interface. Look at that. It says interface because C# has an interface keyword, okay? And this is our inode interface. Look at this. There is input pins and output pins. They're properties. They have a getter. And now we have enumerable of RwLock of ipin. Wait a second. What did Sonia just do here? What is this RwLock? This doesn't exist in .NET. Yes, because Sonia has created something here. The RwLock is an interface which has a generic type parameter, t, which is out, meaning it's covariant. Okay, that's an interesting one. Now, there is a class, read-write-lock, which implements read-write-lock t, okay? And let's see how this is used. This is our source node class, okay? In the source node class, you have only output pin. And this output pin is of type read-write-lock of output pin t. So I have mirrored the classes from our C++ and Rust into C#. I did exactly same design as I have in those other languages here in C#. I also have read-write-lock and output pin, right? Wait a second. C++ has things like scoped locks. Rust has also this kind of thing, right? So what about C#? How do I do this? Let's see that. So for example, a C# implementation of connect will set the connection to the output pin, which is, in this case, in this implementation, I put here read-write-lock of output pin for this connect. I just chose this type for the parameter of connect. So I'm assigning mConnection to be output pin, okay? So mConnection is the read-write-lock of output pin. As you can see, I also have mSelf because I need the read-write-lock to self. I cannot convert this, which is an input pin, into read-write-lock of input pin. I have to have mSelf, okay? So for that, I have read-write-lock from this. This is an interface. Let's check that one. This is an interface, very similar to our C++ version. Let's look at the C++ version. You see our graph input pin is enable read-write-lock from this. This is the class. And this is the equivalent in C++ of what we're looking in C#. So it has this pointer to self, mlock. And it has this method lock from this to set it. Let's see at the C# version. In C# we have read-write-lock self. It has a setter, so it's a set property set. There is no get, only set. We don't need a getter, I suppose. So this is our input pin, which implements read-write-lock from this. It has this no label mSelf, which is read-write-lock input pin t, which is read-write-lock holding this. And this is the implementation of this property setter. So read-write-lock self set. This is super cool, right? Straight into the expression, no need for curly brackets, Scala way. Let's do it in a Scala way. C# is becoming Scala these days. All right, so this is our assignment to himself of the value, which is read-write-lock containing this. All right, so we have done the same thing in C# that we've done in C++. Let's look at other things that's happening here. We have this connect method, and it takes this connection, okay, that we just assigned here, and we say here width right. Okay, what is width right? You can see, let's see the C++ version of that function. We can see that the C++ version of the connect method in the input pin is actually taking graph output pin. Okay, it is the try connect that takes read-write-lock, and I read-write-lock the interface to iGraph pin. Okay, so that's a try connect. But in C#, I don't have the try connect implemented. I implement just connect to take the read-write-lock. Okay, so let's look at this try connect then. You can see that the method calls try write on the other pin. Okay, so it says I have this interface to the lock to the other pin, and I want to try to write to it as graph input pin of T. Okay, so that's acquisition of a write lock. This will be this write lock guarded input pin. Okay, so the other pin. And once we have this write lock guard for the input pin, we can call connect on it. Okay, let's see the C# version. In C# version, we just say width right. This width right will acquire the lock, and under the lock, this lambda is going to be called. And once the lambda finishes, the lock is unacquired. But how is this implemented? C# has special construct in the language. Using. Using is an interesting construct in C# language. How do you use using? Using requires that the expression in those braces evaluates to Disposable. That's the trick. So you could think that, oh, I just did the lock, unlock, and they call the lambda in between. No, I'm using this magical using expression, okay? And for that, this lock guard needs to implement that Disposable. So what does the write do? You see, we're calling write. So this write is actually returning us write lock guard. Let's see what write lock guard is. It implements iLock guard interface. Let's look what that is. iLock guard is covariant with T and allows you to get T from it. The write lock guard is an iLock guard, and iLock guard is Disposable. So write lock guard has to implement dispose method. So this dispose method is a destructor, an equivalent of the C++ destructor. And if you ever used C++ CLI, which is a binding layer between the native C++ and managed .NET, for example C#, the way the dispose is implemented in C++ CLI is destructor. It's actually destructor. So if this is a C# class, the Disposable, Disposable is implemented by putting a dispose method. But in C++ CLI, you just implement a destructor. That's what you do in a managed class. So this is equivalent of the destructor. So we can see that in constructor, we acquire the lock, the writer lock, and in the dispose or destructor, we release the write lock. Okay, I have a separate write lock guard, and I have a separate read lock guard class. Because this is C#, it's not so easy to make it just one, okay? So, it's a different method call here. So, yeah, so I have two classes, read lock guard and write lock guard. In construction, we acquire the lock, and in destruction, we release the lock. We also support timeout here because this method takes a timeout, and it's actually passed into this lock guard. We can see that this with write and with read actually takes the timeout, so we could specify a different timeout for each operation. For example, if we want to connect two pins, maybe there is a smaller timeout, and maybe disconnect pins, maybe different time. I don't know. There might be reasons why you want a different timeout, right? So I have this with write and with read, and the reason I have those is to convert using into a functional construct. That's the only reason. So as you can see, for example, this using here, because this using here maybe not so much, but this using here is a kind of like is breaking the functional flow here. If I have a call to a method that returns something, and I have to make this call inside of this using, then I cannot put it into, for example, LINQ expression. And with this widthWrite, which is wrapping it into a function, and you call this lambda inside this using now, okay, here, and return from the whole thing the value, okay. Now I can compose it with LINQ expressions. I just show you now. For example, I have a LINQ expression here for disconnect. And this is the LINQ expression. LINQ expressions are a pretty cool thing in C#. You don't have them in Rust. You have those kind of like LINQ methods. Like, this LINQ expression can be rewritten as, let me just write it again, equals connections, select, perhaps select, yes, okay. So for every X that is a connection, widthWrite, yes. Oh, look at this. Some AI is helping me here. It guessed it. You just rewritten this whole thing here as a select. Amazing. AI is helping me. Long story short, this expression, connection select, and then this lambda here, is equivalent to this LINQ expression, okay? So you can do either of these two, okay? So whichever you prefer, it's your personal preference, which one you want to use. But the bottom line is that this widthWrite is now composing. So I can use this lambda and it will be called under the lock, and the result of this expression will be returned, and this select will use this result, will select it as an output of this, enumerable that we put here in this action. So this action is becoming enumerable of those t's, okay, of those selected t's. And we selected the results of this disconnect. So disconnect is a deferred action. Oh my God, another thing we just imported from our other solution here in C#. So I was actually thinking, do I need a deferred action? Let's see what deferred action is and how do we support coroutines. All right, let's see. So deferred action is an abstract class. So in C# there is no enums like in Rust. You cannot have like enum with value in it. Okay, you cannot do much. You can do some kind of hacky way of unions, like you can use layout structs and force fields to be in the same bytes in the same address, but you cannot actually make a nice decent unions. Okay, so the prescribed way, as far as I could find on the net, because I was curious if it is even possible, this is the prescribed way. Just define class hierarchies. That's what C# is about. You just need classes. C# is all about defining lots of classes. So let's define some classes. That's our deferred action. Now, in order to support execution of coroutines, I have this abstract method run, which returns a task. What is a task? Ha ha ha. Let's see what the task is. So in C++ version, what did we have? So this is C++ version, and in the C++ version you have a promise and coroutine. All right? Bear with me. This is an example use of deferred coroutine in C++. So I have this deferred coroutine. It is deferred. Now I have this lambda here, okay? And this lambda is returning coroutine. So the return value is a coroutine. And this deferred coroutine is taking coroutine. So I have to call this lambda straight away in line. I have to call it. And when I'm calling it, I'm getting a coroutine. Okay, so the return value is a coroutine, but what is the lambda if it's not a coroutine? So, this code here between these curly brackets is not a coroutine. That's not a coroutine. That is a promise, okay? That is this guy, promise. And when you call operator, the getReturn object is called, okay? So yeah, so you have a promise and you have this coroutine. Now, task is a coroutine. Now, then what is a promise? So this is our C++ code process backwards. And in this process backwards, this is our promise, right? So we got input pin, read lock, propagate backwards, and then co-await, but after releasing the read lock, okay? Let's see how that looks in C#. This is our C# version of the process backwards on the transfer node. Guess what? we call propagate backwards on the X that we receive from the with read on the input pin. Okay, so that gives us an action. Let's look again at the C++ code. This bit here, right, we call propagate forwards using the read lock on the input pin, and we get this propagate action. Okay, and then after we release that lock, we await on this propagate action. Okay, and here we do the same. We get the action and then we await, but we have to await on the task because this is C# and you have to await on the task. So I have a run method that gives me a task. Okay, so this is a deferred action. So this action is a deferred action. And then deferred action can give me a task when I call run, and I can await on this task. Isn't that brilliant? So let's see what are the deferred actions there. There is a no deferred action, and run returns a completed task. There is a single deferred action, and run will just call the action, and the action itself will return new deferred action. So that new deferred action needs to also be run in order to continue the chain. Remember our run actions in C++. This is our run actions in C++. We pass it an action. If this action has a value, then depending on the type of action, if it's a single, okay, we call it, and the return is a new action. And this new action goes back to this while loop, and we keep calling until there is the next action, okay? So you can see that here what we're doing is we're calling this action here in the single action. It returns some next action, and we run that next action, okay? So that's not perfect because here actually we will build the stack, okay? So that's not the best implementation. So it's not perfect, and there is a space to discuss this because, quite frankly, I'm just thinking, what is this deferred action? If deferred action is by any chance not simply just task, I was thinking maybe I should replace all those with just tasks, you know, because we'll learn about it in a second. Let's see deferred sequential. Deferred sequential, when we run it, it runs for each loop, awaiting on each action in actions, which is an array. Okay, so we run each of the deferred actions and we await on this in a loop like this. So this is our sequential. Okay. Now, an interesting thing that I wanted to point out is that this is a promise, and task, which, as I said, is a coroutine, is a result of calling the promise. Okay, so we have this promise, and when we call this promise, we're getting the task, a coroutine. It's very much the same as in C++. And here we have parallel, but parallel will be different. Okay, I'm using here some LINQ expression again. I'm just saying from actions, select action run. And this way I'm getting an enumerable of tasks. And I can use task when all, passing this enumerable of tasks. Okay, it will create a new task that is awaiting for all children tasks to complete. Okay, it's not only going to await on them, it's also going to poke them to go forwards, you know. And we have this deferred coroutine, and as you can see, it's just a task. Yeah, coroutine is just a task. So the question is, do we need those deferred actions? Perhaps everything can be just a task, because .NET gives us tasks. We can explore that at some stage, but for now we have this deferred action and these 4 classes here to mirror our implementation in Rust in C++. This is our C++ version. In C++, action is an optional of actionable, and actionable is a variant of single, sequential, parallel, or coroutine. And we just wanted to achieve same kind of, you know, design in C#. So that's why we have those classes. But the good question is, do we need them? Because in C# it seems like all of them is just task. In .NET it's a task. All right, so in our C# version of disconnect for the output pin, We call disconnect all the connected pins. They give us actions. We collect all those actions using this LINQ expression into this actions enumerable. We freeze it, this enumerable, it needs to be frozen into array or list at this stage, okay? Frozen meaning that this expression needs to be fully evaluated. And once it's fully evaluated, then we can pass this array into deferred parallel. And then this deferred parallel will run those tasks in parallel. And it will happen when we call run, because task.whenAll will run those tasks in parallel. So our C# implementation of the transfer node process backwards method will create the asynchronous function, which is a promise. And that will take the input pin, will get the read lock, and under this lock it will call propagate backwards, which will return deferred action. And then we call on the deferred action run, which will return a task that we can await on. While we're awaiting, the lock is gone. Then we acquire the write lock on the input pin. We receive the data into the input pin. So the received data on the input pin will go to the output pin that's connected to it and receive data from that output pin into this input pin. So this input pin will go to connected output pin of the source node, for example, and it will take the data from here and it will receive it. Okay, so that's why we're locking for writing this pin, because we're changing the data on this pin. And the next thing we do on this lock is just return data on that pin. Okay, and this is the lambda expression that is evaluated under this write lock, and the result, this value of this data, is returned from this lambda expression to the caller and assigned to this variable data. And now outside of this lock, so this write lock here is already gone here, okay? And now we can call function while not holding any lock. So that's a good practice to release all the locks when you're not doing things related to data, that's under the lock. So we got this data already. We're no longer talking to the pin. Now we just have a data for ourselves, and we can pass it to a function and get the result. Okay, so that doesn't require any locks. And now the result needs to be set to the output pin of the transfer node. So we need to set the result data here on this output pin of this transfer node. And as you could imagine, we call on the output pin with write. Okay, so that will acquire the write lock. And under that write lock, we're going to say set the data to be result. Okay, and that's it. And that's our write lock. And after this line, write lock is gone. Voila! Everything works. Right, let's see if that actually works. Run it. Bang! It works. But what are we seeing here? So I have created a NodeGraph very much the same way I did it in Rust or C++. I created these 5 nodes, 1 source node, 2 target nodes, 2 transfer nodes. I put them into a NodeGraph object. Okay. So this is a NodeGraph class, which is essentially a hash set of inode, okay? And then I have connected the pins, okay? So I take source output pin and I connect it to transform input pin. When I'm connecting, of course, I have to do it on the lock. So source output pin needs to be locked for writing, and then inside this lambda, in the same fashion as previously I showed, we called connect on that pin, okay? Because here this lambda is going to evaluate under this write lock on this pin. So we're essentially calling connect on this pin under the write lock, and so on for the other pins. And that creates this graph, okay? And we return a source node, target node 1, target node 2. So we return this, and the reason is because we want to load value into the source node and read the values from the destination to see what is the result. So our run function calls build graph. We get the tuple of source node, destination 1 and destination 2. Then for the source node, we query iValue loader of ints, and I have a source loader. And for destinations, we query iValue holder for floats. Okay, so we have those 2 target holders. And we also take the source output pin to confirm what is the value on the source node output pin. So when we load the value into the source node, it should go into this output print of the source node, so we want to be able to read it from there. All right, so what happens next? As we can see, we load the value 5 into the source node, and then we process forwards, we print something, then we load some other value, okay, and we process backwards. We use task wait all, destination 1 and 2 process backwards, so this will run in parallel, okay, and then we print. So what did we print? Result of processing forwards 5 gives us 2.5 and 7.5, and result of processing backwards 7 gives us 3.5 and 10.5. And what was the formula for this? So the transform nodes we have created have formulas x divided by 2 and x multiplied by 1.5. So 5 divided by 2 is indeed 2.5, and multiplied by 1.5 is 7.5. 7 divided by 2 is 3.5, and multiplied by 1.5 is 10.5. So we can see that the node graph worked correctly, nothing crashed, everything works fine, nothing deadlocked, everything just worked, right? So yeah, so this is our C# implementation of our node graph, and it mirrors very well our implementation in Rust and C++. We have an implementation of this deferred coroutines in C# now, and they're essentially just tasks in C#. So I feel like in Rust it would look the same, okay? So the code will be very much the same as here. Let's see. We'll see that in some next episode, in the season 2 of C++ versus Rust. And this was C++ versus Rust C# special, because we need to C#. Comment, like, subscribe, and stay tuned for the next episodes and season 2.